and how it's solved, but it's encoded inside of something else.
There's many situations where there's going to be a closed form, and of course you always want to use the closed form version.
Well, not always. So sometimes for scalability, like for incremental grade descent, right? If the number of parameters is far less number of data points, and I believe they're randomly ordered, then I probably would converge before I would even read all the data. Right? So think of the data's on disk, and it doesn't fit in memory to get it. And I can converge to a solution by reading block after block from disk, but I can read through 5% of the blocks, and I've already converged.
That makes sense.
I don't have to read any more things from disk.
Whereas a closed form solution, you'd have to use all.
Yeah. Not only would you have to bring it in memory, I mean, there are other ways around this, but you know, in the way I showed you, you would have to bring it all to memory, but then actual inverse calculation involves kind of other steps that are kind of even, you know, just the memory might be kind of d squared, right? But the runtime might be cubed.
I see.
Right.
It's more of like a runtime thing.
So it's more of a runtime thing, and so yeah.
Okay. That makes sense. Okay, thank you.
Sure.
Yeah, I'm glad it actually makes sense.
Okay, good. Yeah, no, I mean, all the things you're thinking are quite reasonable, and they are used in some cases.
Oh, right. Did you get my address?
Are you sure? Yeah, because it's 1 minus y minus 3.
So, yeah. I noticed that.
Great, so let's get started. Hopefully homework 3 was okay. I think I have homework 4 almost ready. I just need to kind of wrap some stuff up and post it. It should be posted by the end of this week. And then we've been talking about the singular value decomposition, the SVD. And so I like to think of this SVD as starting with a column thin matrix A, where it has n rows and d columns. Everything works fine if you have, you can just, everything is kind of symmetrized in some way. So if there are more columns than rows, just other dimensions change, but everything still makes sense. You can swap the rows of the roles of the rows and the columns. But this is a decomposition into the product of 3 matrices. The first one is U. The second one is S. U is n by n. This one is n by n, and this was is going to be orthogonal. S is so diagonal, which means that there are only entries here, which are interesting. Everything else is 0, and you know, since this is all 0 in languages like Python, they don't even report this part of the matrix. And then you have some D by D matrix, the transpose. In Python, when you call this, it's actually, you get the transpose return. Sometimes you return V, and then you have to transpose it if you want to make this product to put stuff back together again. And then to review, a column of U, call this UI. This would be the ith left singular vector. This guy here, we'll either call it SII, or maybe just sigma I is going to be the ith, so it's singular value. Okay, and these have the property that sigma 1 greater or equal to sigma 2, and they're going to be greater or equal to 0. And then the row of V transpose, this is the column of V, is going to be the ith right singular so vector. Okay? All right, so this was this singular value decomposition. We talked about some of these properties. Some of those I will review today, and then we'll talk about more in relation to some other stuff. Yeah.
So is the SVD used for just PCA analysis and data analysis, or does it have, or does it do, like, why would we want to use the SVD?
So kind of the canonical use of it is for principal component analysis. As you'll see next week, Wednesday, I think, is when I have this scheduled to actually solve PCA, which is finding the best subspace approximation. You basically have to do some operation called centering the data, and then the singular value, the columns of that give you the principal components, give you the basis for this. So it's like very directly used there. However, if you look in the textbook, I outline like at least two other ways that it's used. One, I think we'll see also on Wednesday, called multidimensional scaling, which is a slightly different problem where you're just given a set of pairwise distances. And you can do some linear algebra to convert it into something else, and then you take the SVD and out pops an embedding of those points that are close to those, that the distance between those points are close to the ones that you've been given, right? But again, the SVD is the operation you do. There's something you want to do. I want to take two data sets in high dimensions, which I know have an alignment with them, like kind of, and how do I find the optimal alignment between them under, say, a rotation? It turns out you do a couple of operations. You take the SVD and out pops the answer, right? It shows up in kind of a variety of places. There's things for if you have missing values in your data, you typically use the SVD as the core thing that helps you give the best guess of what are the missing values. And it's used, but you have to wrap it in some other stuff. So this SVD comes up like all over the place. It is kind of it's a very, very common operation, right? So it's not just for this problem, but this is kind of the canonical problem. And I think it encodes a lot of the intuition of what's going on. It's finding the subspace in your data. And as we'll see today, I think we'll see today, it's connected to the Eigen Decomposition, which you may have seen, and that has these applications from signal processing to all the other places. It's basically the SVD is kind of effectively the Eigen Decomposition is a special case of SVD, right? So it's really this thing that just kind of shows up all over the place. So yeah.
So maybe like we can kind of decompose the name. Why is it called singular value decomposition? What is this supposed to be doing?
These are the singular values. These are singular vectors. The decomposition of this matrix into three parts. That's what decomposition means. In kind of numerical linear algebra class, you'll go through a bunch of other decompositions of a matrix. There's a kind of UV decomposition and all these other ones. So that's what decomposition means. It refers to that. It gives you these so-called singular values. That's what the name comes from as far as I know.
So singular just refers to the values on the diagonal, the scalars in the diagonal?
These are called the singular values. These are called the singular vectors.
Okay.
What does,
Because they
why it's singular? They, I kind of know a story for Eigen Vectors. I don't know the one for singular. That I guess kind of means self in German, and it, we'll see, it's kind of, you get yourself back by doing some operation. What's singular, they're kind of unique in some way. It gives you a basis in RD or in RN, and it's kind of unique, but as long as these are distinct. If these are distinct, if the singular values are distinct, then the basis it gives you is distinct, and maybe that's what singular refers to. But it's also singular in its power in data analysis. So there, you could think of it that way. There's not another kind of operation that shows up as kind of pervasively as this one does, which is why I'm spending so much time. All right, so one of the things we did at the very end of class is I went through a demo in Python where we kind of stepped through a small example, and I want to go through that again, just a little bit more slowly, and do it on the board. So we start with the matrix A, and this matrix was for 3, 2, 2, minus 1, minus 3, minus 5, minus 2. Okay, and I can actually draw these points. So I can think of these as n 4 points in 2-dimensional space. So the first point has x coordinate 4, y coordinate 3. Right, this may be A1. This one has 2 and 2. So it might be right here. This might be A2. The next coordinate, minus 1, minus 3. A3 is down here. And A4 is minus 5, minus 2. 4. Okay, these are 4 points in 2-dimensional space. Something that I chose this specially so that all of the columns add up to 0. Okay, this is what's called, this matrix is centered. All the columns are adding up to 0. So the average x coordinate is 0, the average y coordinate is 0. Things make more sense when they're centered, and we'll revisit this next week with PCA. Okay. Then I can write down the SVD of this matrix. Remember, I get U S V transpose equals SVD of A. And so U is going to be 4 by 4. I'm not going to write down U, but I'll write down the other ones. These will be more informative. S is going to be basically 8.1, 0, 0, 2.3, 0, 0, 0, 0. Right? So it's only values on the diagonal. Everything else is zeros here. And then V is going to be, let me write down V transpose. It's going to be minus 0.81 minus, right up to 0, minus 0.58. This is going to be minus 0.58. And this is going to be 0.81. Turns out V transpose is equal to V here, because transpose only swaps these two. It doesn't change stuff on the diagonal. Also notice every row and column is going to be a unit vector here. So if I square this, I add them up, they're they're more than 1, but if I square them, it kind of decreases the value, right? So this squared is like 0.28, right? And this squared is like 0.6 or something. And something like adding those up should be equal to 1. And I've taken off some decimals there. Okay, so now I want to think about this as in this space of the bases here. And so there's some small circle here. And I want to draw on the circle a few things. Let's start with some data point. X equals to 0.243, 0.97. Okay, so this is almost so this is almost the unit vector. It's going to be about right here. Okay, so this is x. Okay, next I want to draw the rows v1, v2. Okay, so v1 is going to be, let's see, minus 0.8 minus 0.6, right? So it should be a unit vector. That's about here. This is going to be v1. And v2 is going to be orthogonal. So it's going to be minus about 0.6, positive about 0.81. So this is going to be, so this is a vector which is orthogonal here. Okay? So now I want to trace what happens. So what'll be interesting is I want to kind of evaluate this, right? I want to say a times x. This is going to give me, x is 2-dimensional, a is 4 by 2-dimensional. So this is going to be a 4-dimensional vector, right? So eventually I'm going to get out this 4-dimensional vector y here. And I want to figure out what happens as I do, well, this is going to be u s v transpose x. So I'm going to first compute this value, and I guess this one's going to be xc. I don't know why it picks something so complicated. Let's call this p. SVX transpose is going to be q, and then I multiply by u, I'm going to get out y. So let's kind of do this step by step and see what's happening here. Okay, so the first thing to do is I want to do x times v transpose here, right? So I want to look at v transpose times x, and okay, I'm not going to do the calculations. What I'm going to say is if I multiply x by here, I'm basically taking a column x, and I'm doing a transpose, and I dot product with this, and I get the first coordinate. This is a dot product with this vector. This vector v1 is here. So basically, it defines this subspace, and I'm going to project x onto here, and I'm going to get the length in this along the v1 direction of x. It's going to give me this value. What roughly is this value going to be? Conveniently, I didn't write that down, but okay. So let's see. I mean, this value will be about, let's say, negative 0.7, something like that. Roughly negative 0.7. Yeah.
In the VT, those are always orthogonal.
Yeah. So these have to be orthogonal. These are the right singular vectors and the left ones, right? The right singular vector ones are orthogonal to each other. Yeah. Because it's going to be an orthogonal basis. I get it out of here. Okay, so what does this mean? Well, it gives me a negative value here, and if I go the other direction onto V2, this one is going to be about, let's say, 0.5, something like that. Okay. And so when I do this here, what this has done is it's changed the basis. I'm going to get values which are still going to be on a unit circle here. Maybe I'll make this a little bit smaller so the next drawing can be easier. Okay, so I'm still on a unit basis here, which means that V1 is actually, think of V1 as being here, and V2 as being here. And now the new coordinates are going to be in terms of V1 and V2. So in terms of V1, it's going to be negative about 0.7, and for V2, it's going to be positive 0.5. So it's going to give me a point about here. So this is going to be the point P. What I've done is V1 and V2 are orthogonal. That means they give me a new basis, and all by multiplying by orthogonal matrix here, I'm just translating this point x into this new basis. The first coordinate V1 is negative, the second coordinate V2 is positive. But it's not changing the norm. It's still on the unit circle. Okay, I'm not changing the norm of the vector P, but it's in a new coordinate system. It's now in the V1, V2 coordinate system instead of in the original basis coordinate system. Okay. So then the next step here is going to be doing S. Let's write it. This is here. S V transpose X, and we'll say that this is going to be equal. This is going to be equal to Q. Okay. So what is this S matrix doing here? Let's just look at the top half of the X matrix. It's basically scaling on these coordinates. So the first coordinate gets scaled by 8.1, the second one by 2.3. So it's basically taking all the points on this blue ball, and it's kind of stretching them out to going 2.3 up in this kind of the V2 direction, and 8.1 out here. Right, so it's going pretty far out here, and there's going to be some sort of ellipse. Right, so there's some ellipse now. Let's make that a little bit darker. This is tricky if you're trying to do it at home. You have to move your feet to move the marker. Okay. Okay, just don't appreciate it. All right. Okay, and so what's going to happen is it's going to scale this point P to be, it's going to kind of push it out here someplace. This is going to be, this point is going to be Q. It's going to be on this ellipse now, and Q is going to go out up here. It's going to kind of stretch it. Okay, now this is an ellipse, and if you thought about the geometry of ellipses before, they are defined by some basis, and then a stretch along this basis. So if I wanted the ellipse to be in a weird angle, I would have to define the basis that way. So in fact, there is kind of a basis here. This ellipse in this picture looks kind of like this, right? It's on this. It's kind of on this kind of twisted basis, and this basis aligns with V1. The long direction is V1, the short direction is V2. Right?
I'm confused a little bit. How do you get this ellipse? Where does this ellipse come from? Just the singular
It's a
vector?
stretching of the x coordinate, or the V1 coordinate by 8.1, and stretching of the V2 coordinate by 2.3.
Gotcha.
Right? And if I just stretch the original x and y coordinates, I'm stretching in the wrong, I can't get this oddly shaped ellipse. And I want this shape ellipse because the data is kind of distributed this way. This is the biggest variation of the data is along this direction, which is what the top singular vector is capturing. And then once I factor that out, the most next correlation is on the second one, and so forth. There are only two, so it turns out it's the least direction, but yeah.
So can you think of the S then as like a scaling, like
Yes.
the transformation on the, would it be correct to say like on the matrix? Or like
All the scaling component of the matrix is described within S. Okay? How that is scaled from the right side is described in V, from the left side is described in U. I'm rotating the basis so that I can scale along the basis I've described. Right? So the thing of either way, there's some scaling here. From U, like there's something missing. I've also scaled along these two other coordinates. Think of, there are two coordinates coming out of the board here, but the scaling there is 0. Effectively, the data has no variation out here. I could draw these data points in this new basis, right? And they would be two of them would be positive, and like I'd have A1 and A2 would be up here someplace, A3 and A4 would be down here someplace. But they would be directly in the board, even though there are now two more coordinates coming out of the board. Okay, and then U is just rotating it, the scaling. How much of the scaling is attributed to each of the data points? So I would, to think about it from the left side, I would kind of do a transpose of this matrix and do the same thing. Then there are two data points, but they each have 4 dimensions. Or you can think of it as how much of this scale component is contributed to by A1. And that's what the kind of what the contribution of this row is here, and the coordinate, the first element of that row, tells you how much is associated with the first singular value. Okay, so this is kind of what it's doing is it's kind of capturing, you can think of it as capturing, the V is capturing the V1, the direction with the most variation in the data. And so, but it doesn't tell you how much variation is there. That's what S11 tells you, how much variation along that direction. Okay, and then once I factor this out, the V2 has to be orthogonal. It finds the direction with the next most variation, right? And then how much variation is there? It's 2.3 or S22. Okay, so this is kind of a geometric way of thinking of what's going on here. Now let me kind of describe this more linearly algebraic way of thinking about this. And kind of get you to, where should we go? Let me start writing this up over here. So I want to kind of translate this back to why is this the sum of the squared errors here? And okay, so now okay, so I want to write this property in a different way. I want to say that A times V1 squared is going to be equal to S the transpose. So this is true for any value x. So for any value x, this is for all x in Rd, right? Or A is n by d. This is going to be true, where the norm of ax, right, which is all I've drawn up here. I started with x and I get this vector q. The norm of this q is going to be equivalent to a times x. I've only done x v transpose s. U is an orthogonal matrix. The orthogonal matrices does not change the scale of the vector when I multiply them. It's just kind of rotating the basis. It's not changing the scale. The same way v did not change the norm of the vector, u won't either, so this is true. Okay, so I want to find, so now my goal is to find v1, so which is going to be in Rd, and the norm of v1 is going to equal to 1. That is going to maximize a v1. All right, so I want to find this. The one with the most variation is going to be this. This is going to be the first singular vector. Okay, so I can define the first singular vector as the vector that's a unit vector which maximizes this. And if I know I have this decomposition, I would argue that this vector, I can call this v star, that v star equals v1. Okay, because so v, the norm, so if this is true, then I can say the norm of a v star, let's just write v, is going to be equal to the sum of j equals 1 up to d of sjj. Let's just say it's squared here. So let's simplify computations, times the dot product of vj times, let's call this x squared. Okay, so I know that each of these terms are going to be orthogonal to each other. And so as I am going to be, as x aligns with different vj, it's going to decrease the alignment with each of these. I don't have this whole argument in my notes or mapped out in my head, but this is because the largest singular value is going to be the first one, then this is going to be, there's some steps in between I don't remember right now, but this is going to be, it's going to be maximized when I have the most contribution along sjj. S11, which is the top singular value. Okay, and I'm going to get this property that v1 is going to be equal to v star. So I want to go back to this task we had before, where we wanted to find this this subspace F, which is going to be a k-dimensional subspace, where I'm going to define by these vectors. I'm going to call them W now. W1. This is going to be a basis up to so WK. And I want to find this subspace that is going to minimize A minus the projection onto F of, let's say, this sum equals I up to n, AI squared. Okay, so this was the sum of the squared errors thing that I want to do, and I want to kind of argue a little bit more formally now using effectively these properties that this is going to be defined by the top k right singular vectors here. Okay, and I'm going to use the property that that if I do A times Vj squared, this is, remember, this is equal to S V transpose V squared. And so what this does is this just gives me the Sjj squared. This gives me the jth singular value squared. So if I multiply A by the jth right singular vector, the norm of this is just getting coded in this, the jth singular value. Okay, so now if I write, if I expand this for any x, I can now say x minus projection onto, and now let's define this where WF is equal to V1, V2, up to Vk, where these are the right singular vectors. Right, then this term is going to be equal to, I can write x in this new basis, I equals 1 up to d of okay, so this recovers x, but I've written it in the basis of all the right singular vectors. So this is going to recover x exactly. I've just written this in the new basis. Remember, each of these VIs is going to be a d-dimensional vector. And I'm just saying the contribution along this basis. So this is, I'm saying, if I go back to this picture, the x is written as the negative 0.7 contribution of V1. You know, so I take this vector I here, I get x is written as the 0.5 times V2, I get this point here. I add these 2 points up, they get to me, they get to x. Right, so I've just written x in this new basis, I've recovered x. And now I want to recover projection onto f of x. This is just going to be the top k of these. Okay, so if I just project onto the top k, then I'm going to get the projection onto f. So I've just written the top k things here left, right? So what's happening here is that I've got some point x. If this is v1, this is v2, or think of this really as the top k things, I can say x is here. I can project onto x here, and I get this component. This is the representation of the top k. This is the representation of everything left. Okay, if I want to know the norm of x, by the Pythagorean theorem, this length here, the length here of the norm of x, is the squared length is the sum of this squared distance and this squared distance. But that's going to be true under any basis I have. So if I had the original, right, if you remember the norm of x, if I use the original basis here of x, I can say the squared norm of x was the sum of this squared quantity plus the sum of this squared quantity. But if I change the basis, the norm is the same. It's still this squared quantity and this squared quantity. Okay, so, and I can actually say, well, I'm going to just look at, let's say this is a k-dimensional subspace and this is d minus k. I can project it, I can draw a two-dimensional picture with the x and these, or the origin and these 2 points here. There's a two-dimensional picture that's perfectly valid. And I can decompose the norm of x into the component along V1, or the k-dimensional subspace, and V2, or the d minus k-dimensional subspace. And so the norm is preserved. This is the norm captured in this projection. This point here is in general the pi of f of x. And so its norm is here. And so what's left over, the difference between this squared norm and this squared norm is going to be exactly this squared norm over here. This quantity is exactly here. This is going to be equal to the sum of I equals now k plus 1 up to d of vi dot vix. Which is this quantity left over here. Okay, so I can, if I do a projection, I can decompose the norm of any point into the length of its projection, or its squared norm. The squared norm you can decompose by the Pythagorean theorem. The squared norm is the sum of this squared distance plus this squared distance. Okay, so if I want to minimize this squared quantity, this squared quantity of x is fixed. So I want to maximize this squared quantity. And I can maximize this squared quantity by picking the top direction v1, and I've collected the squared norm s11 squared. Right? And then I can collect, and then I need the next basis to be orthogonal to that. So v2 is going to be the one that maximizes the subspace that's orthogonal to v1, and I collect that. And I do this k times, and then this is everything that's left over. This is the residual, is the same as this distance right here. Okay? So the nice thing about it is this quantity is actually going to be equal to I equals 1, k plus 1 up to d of SII squared. This is if I sum over all the data, right? So now I can say, let's look back at this problem here, right? So now I want to sum over all the data. I equals 1 to n. And now I let f is defined by the kind of the k-dimensional subspace defined by the right, top k right singular vectors, that this means that this is going to be equal, sum equals I equals 1 to n, sum j equals k plus 1 up to d of ai, let's see, of vj dot product vj ai. Okay, now I can swap the order of operations. I can now sum over j k plus 1 up to d I equals 1 to n, right? I get this same thing here. I've just switched the order of the sum. But what's nice is that now this quantity here is going to be equal to sjj squared. This is, I'm summing up the contributions of every point AI. This is a unit vector, so I can factor this norm out. Right, so I'm just getting this dot product left. Right, this guy actually, this is a scalar, this is a unit vector, this goes away, and it's just the sum of these dot products, which is just the variance, and that's the variation along here, right? So I've gotten this term back out. With, if I plug in x, where is it written up here? But okay, but I'm getting back out the singular values here. So the sum of the residuals, the sum of the squared residuals is going to be exactly the, that's the term inside of here. So in general, this is going to be equal to j equals 1 equals from k plus 1 up to d of sjj squared. So the sum of the the squared singular values from k plus 1 up to d is going to be this residual term here defined on all the data. Okay, so let me go and summarize these kind of important facts here. All right, so where Vj is the j right singular vector, then we'll say that the norm of a Vj squared is going to be equal to sjj squared. All right, so the amount of variation that's in this direction, the jth right singular vector direction, is going to be the squared singular value. This is going to be equal to the sum I equals 1 n of say just the Vj AI squared. Okay, so what's going on here is I've got some data points here. I've got some basis, and I pick Vj to go in this direction. I project, and so it defines this subspace here. I'm going to project all of A on here. And now I've got one-dimensional points here, right? All these points, this point, if this is A7, then this is basically Vj dot A7, right? And so this is going to be a value that's going to be, in this case, maybe this is negative 0.9, right? And so now Sjj squared is going to be the variance of this data set projected onto this one-dimensional subspace. Okay, so this is going to be the variance of the set of Vj kind of for all I equals 1. Right, so I'm going to find the set of these points projected on this one-dimensional space, and this tells me the variance along this direction. Okay, and V1 defines the direction with the most variance, and V2 the next most variance that's orthogonal to the first one, and so forth. And Vd is the least variance. Okay. Then kind of the next thing to think about is what's called a rank K or approximation. Okay, so I want to find a matrix B which has to be, its rank has to be K, and B is going to be in and I want it to be and I want so that it's going to have a small, when I look at the norm of A minus B, right? So they have to have the same kind of the same dimensions to subtract here. And by norm, I could mean either the 2 norm or the Frobenius norm. Yeah.
Dumb question. AI. What was AI again?
AI is going to be the ith row
I throw
of A, right? So I have A. This is A. It's going to be n by d, and the ith row here is AI. Okay, so I want to find now.
Well, on that, how does it become like the variance? Because isn't there like a term where you divide by the number of variables for variance, like over n?
No, the variance can scale with, that would be like the average variance or something like that.
Isn't it like
It's like
random variable
the
x minus
expected
u
value.
squared?
Yeah, okay,
over
so, right, so it would be like n times the variance.
Okay.
Yes, so it's going to be n times the variance. Okay, so now I want to find a rank K solution, and so this is whether it's the 2 or Frobenius norm, and we'll step through both of these. This solution is going to be a matrix called a K, and this is going to be written. You can write this as what's called UK times SK times V transpose K. Okay, so these, I'm going to, again, get this from the singular value decomposition by modifying each of these approximations. And what's going on here is that I'm going to take this, and it's going to be the first K left singular vectors. So I'm going to basically set these to 0 except the first k. I'm going to keep these fixed in S. This will be SK, this will be UK, and VK will be up here, where I'm going to keep the top k right singular vectors. Okay, so what is this going to look like? This is going to be UK is going to have k columns and n rows. SK will again be n by, it can be n by k here. So it'll be S11 up to SKK, and all this is 0. And then this is only the top k. So this is going to be d by k here. So I've truncated the U, S, and V to only include the top elements here. So the first k left singular vectors, the first k singular values, and the first k right singular vectors. These are rows, because this is transpose. These are columns. And I multiply these back together, and this is going to give me this A sub k matrix. It's also sufficient to only zero out the singular values and keep the rest of U and V. That also works, but the rest of it gets multiplied by zeros. Okay, so this gives me a rank K approximation. It's going to have the property that A minus AK, so if I look at this squared and I look at the 2 norm, the 2 norm is the any vector which multiplied by this maximizes the norm. So this is going to be exactly S k plus 1 squared. Okay, so the 2 norm is going to be the k plus 1 squared singular value, the spectral norm. And A minus AK, the Frobenius norm, is now going to be the sum of J equals k plus 1 up to D of S JJ squared. Okay, so it's going to be the sum of all the leftover singular values from k plus 1 up to D squared, the squared singular values. Okay, if I don't want to square them, I take the square root of either of these. Okay, so what's going on with this one is that I've identified some k-dimensional subspace here. This is going to be this VK dimensional subspace, and then I've got this D minus k dimensional subspace which is left over, right? So this is going to be the D minus k dimensional subspace. And what single direction is going to maximize the variation in this subspace? It's going to be the next right singular vector, which I haven't taken out here, the k plus 1 singular vector. And then I'm going to get out its singular value. And the Frobenius is going to be all of those singular values put together. So that's kind of different ways of thinking about these 2 norms. And so the best rank K solution is the rank K matrix, which is going to minimize both of these, either the spectral norm or the Frobenius. Okay, let me try to explain this rank K business in a different way. Given A, I can also write any matrix A as the sum over J equals 1 to D of sigma SJJ times UJ VJ transpose. Okay, let's think about what's going on here. What is, if I look at this, so if I look at this decomposition, see, this term is a scalar, right? This is the singular value. Uj is a n by 1 vector, and Vj is going to be, Vj transpose is going to be a d by 1 vector, right? So this product here is going to be an n by d matrix. This is an outer product. So basically, I'm scaling basically Uj times Vj transpose here, or this, right? So this gives me an outer product, right? This is basically Sjj times this matrix, and I'll call this, and this Aj matrix, okay, this Aj matrix is going to have it's an n by d matrix, but its rank is going to equal to 1. Okay, if I take an outer product of two vectors, it gives me this n by d, this big n by d matrix, but its rank will have to be 1. So if I did a singular value decomposition of this, right, I'm going to get out the first of this matrix. The first singular value is going to be Sjj. The rest are going to be 0. I can write this as a decomposition into a bunch of these kind of orthogonal bases, and only the first one is going to have any content with it. The rest of the subspace is going to be all have no variation, because I've gotten this by taking kind of the rank of a matrix cannot increase by taking products. The rank of this, if I can decompose into two parts, it's no more than the rank of any individual piece. And both of these are vectors, so their rank is 1. So this gives me a rank 1 matrix. But it's all of the same dimensions as A. And as I add, and basically I'm creating, every time in the sum, every element here is giving me a new n by d matrix that's rank 1, and I add them element-wise on top of each other. Okay, and they're all going to essentially increase, each one, because they come from orthogonal components, are going to kind of increase the rank when they add this sum. So by adding, and all I've done to get this here is I've stopped the summation at k. The first k give me the most variation, and I stop it at k is going to be equal to, I can write a k now is going to be the sum of j equals 1 up to k of s, jj, uj, vj transpose. Because it's sum of k rank 1 components, its rank is k. And if I look at the Frobenius norm of this matrix, the Frobenius norm of this term right here is going to be 1, but this is a scalar term. So the Frobenius norm of just this guy is going to be just Sjj. And when I add together the components, I need to kind of add them in this sum squared fashion. So the squared Frobenius norm of all of them is going to be the sum of these squared terms. And then if I subtract, if I look at this difference here between A and A minus K, what's left is just the summation from K plus 1 up to D instead, right, of these other terms. And so what's left over is going to be these elements from this sum, right, the other singular values which are left over here. Okay, so now the spectral norm, I'm getting, again, A minus AK, so I'm getting just the, right, so if I write this up explicitly, A minus AK now has to be sum J equals to K plus 1 up to D of S, J, J, Vj, or U, J, Vj transpose, right? So A minus AK is just all the terms of the residual from K plus 1 up to D. And so now I want the spectral norm is the single direction with the most variation in it, and that's going to be the K plus 1 singular value that's left over. The single most variation in any one direction. Okay, so by the J right singular vector basically captures n times the variance in this direction. The one with the most variance is the top right singular vector. Okay, if I want to get the best subspace that goes for the origin that captures the most variation, then I look at the top k of these, and that defines an orthogonal basis. Okay, if I want to find a rank K approximation, I want to get another matrix B, which is the same shape as A. Then I take the top k and I multiply them back, all this stuff back together with the use of k in order to get another thing that looks like n times d. And so what this is all the data points projected onto the k-dimensional subspace, but I've left the representation as the d-dimensional points. Whereas if I just look at, right, so if I think of U, K, S, SK, VK transpose, these are going to be in RD. If I look at SK, VK, these are basically going to be in, I can think of these as points in our K. I'm basically, U transforms them back to the original d-dimensional coordinates. This kind of leaves them as this lower k-dimensional subspace. But it's not really changing the norm of the points here. It's just kind of the representation as k-dimensional or back to the d-dimensional points. And you can decide whether that's done inside the S, whether I truncate S or not. Maybe the truncated version of S keeps them k-dimensional. K-dimensional. This is now the representation of the points. This just captures the overall norm properties. So let me erase. That's not quite right. Okay, yep.
So we're maybe I misunderstood what the original goal was, right? But I thought we were trying to get less data points, essentially, right? Or less individual elements in those data points. Maybe I misunderstood that.
Yeah.
We're still coming out with the n by d matrix, and we multiply it by u. Is that right?
Yeah, so good. Okay, so what's going on here? This is still an n by d matrix, a sub k.
Right.
That means I still have n data points in d dimensions. What is the advantage of this?
Right.
So I know that they lie in a k-dimensional subspace. So I know there's some k-dimensional subspace which is described by the first k singular vectors. And the idea is that the other d minus k directions are the ones that are probably noise. The signal, the main variation which describes probably the main structure of the data is captured here, and what the leftover is the noise part. So I want to find the k-dimensional subspace. I think there's, if you remember the example with this teapot that was rotating and I'm changing the light, there are only two coordinates which really are describing what's going on there. I think there's really only two, but I probably got some noise in the sensing process. I want to remove that noise and get back just that two-parameter representation. But I want it to look like the original data. So this one will look like the original data, but it will have removed the noise part of it. All right? Or I can leave it without multiplying by the u. I guess the u maps it back to the data points, but I can project all the data points onto vk. If I project them onto this basis, then I get this k-dimensional parameterized representation. So I can describe it in these parameters, which I hope correspond with rotation of light or something else. Now, this only works if these are indeed, if there's a linear relationship here. This is assuming linearity, and the rotation may not be linear. Probably not, but you can think of there only being two parameters.
So follow on that. So essentially you're saying, like, hypothetically you could transform this V matrix into a new basis and make it smaller essentially. But that's just a lot of work to be able to find what that exact, like, because basically it's on like a plane or some other kind of feature, right? Not everything is, I guess like if you went from like a 5-dimensional thing to like 2 dimensions, everything would be on a plane, but you don't necessarily need to find out what that plane is exactly. You can still apply the technique. Does that make sense?
Yeah, so there are two ways so if I do the transformation like this and I get back AK, right, all the data points are going to look like they originally did, but I've removed the noise, hopefully.
Right.
I can also do a transformation where so I can think of, I have a set A1, A2, up to AN. These are in RD, and I can map these into the projection onto the subspace spanned by VK of A1. And now these are going to live in our K. Well, this is not the projection. Let me say I multiply the projection operation leaves me in the same subspace here. So if I multiply by VK, what I'm doing is VK is going to be or VK transpose is going to be a K by D dimensional matrix. Right, so if I multiply a D-dimensional vector by this on the right-hand side, it's going to transform it into a K-dimensional vector. And this will be the vector which captures jointly across these the most variation. Right, so this is how I would transform it into a K-dimensional space. And these are the original ones, and if I do a projection, which is the operation I defined on Monday, it'll stay in D dimensions, but it removes the noise. And basically, this kind of is I write it just as a matrix product way of getting this projected data set. So I want to preview one thing that will be, I think, reviewed again next week, And that's the connection between Eigen decompositions and the singular value decomposition. And then this will be covered, I think, is planned in the lecture again next week, but let me preview it. So to do an or an Eigen vector V of a matrix A, and now for this to be defined, A has to be a square matrix. So A is now n by n. Actually, we call this B. Okay, so for this to be true, then it must satisfy that B, V times B is going to be equal to some lambda times B, where this is a scalar. Okay, and since norm is preserved here, we usually say such that the norm of V is equal to 1. Okay, so an eigenvector is this vector where I multiply it by a matrix and I get that scaled version of this vector back again. And so this is kind of a property of the matrix that this can be true. Okay, and so I'm going to convince you that for a class of matrices, that these actually exist and that they're connected to the singular value decomposition. Okay, so I'm going to define B, and in fact I'll call this BL, which is going to be equal to A times A transpose, where A is going to be in R n times D. Okay, so now this is going to be n times n, right? This is an n times D matrix times a D by n matrix. It gets back an n by n matrix. Okay, and if this has an SVD, if I know that USV transpose is going to be equal to A, then I can write this out as USV transpose, and it turns out to do the transpose, it basically you kind of, to do transpose of a composition, I reverse the order and I take the transpose of each of the elements. But because V is orthogonal, this is equal to US S transpose, U transpose, right? So this whole, this cancels because the transpose is the inverse. So V inverse times V is the identity, factors out. S times S transpose, well, S transpose doesn't do anything because it's a diagonal matrix. So this is basically going to be US squared. So basically what this means is that S squared is equal to S11 squared, S22 squared, and these are. Okay, so now if I left multiply by V, if I left multiply by V times U S squared U, and V is one of the left singular vectors, then what's going to happen is that it's, if V is going to be, well, let's actually make this U1 here times, this is the first left singular vector times U. What this is going to give is a single vector here, which is going to be 1, because the dot product with the first left singular vector is 1, and the rest are zeros here, because it's orthogonal with everything else. So that means V, so it's going to give me 1, 0, 0. And when I multiply that by S squared, that's going to turn into S11 squared, 0, 0. And then I multiply this by U again, and I'm going to get back S11 squared times just U1, because all the other vectors are going to get multiplied by zeros here. And so what I get is that the first eigenvector is going to be S11 squared, and that and the corresponding first eigenvector is going to be U1, is the first left singular vector. Okay, so left singular vectors are eigenvectors of A transpose, and the eigenvalues of this matrix are going to be the singular value squared. And then it turns out that if instead I do a matrix BR, which is A transpose A, now this is D by D, the eigenvectors of this are the right singular vectors. And the eigenvalues are still the singular value squared. So the singular values and the eigenvectors are basically related to each other. Eigenvectors have to be of a square matrix, and in fact, for them to all be positive, it needs to be of a what's called if all the eigenvectors or all the eigenvalues of A are positive, this is called a positive definite matrix. And in this case, if A is full rank, then and D is less than A, then they will all be positive for this one. If they're all positive or 0, then it's a positive semi-definite matrix. They could be 0, and that's the case here if D is less than N. Because then the last ones are all going to be 0. I'm only going to have D ones which are non-0. The rest will be 0. Okay, so the eigenvectors and the Eigen decomposition is kind of giving you a set of these vectors which are orthogonal and the corresponding values. And that allows you to reconstruct B as kind of you can get a decomposition of those as well. Okay, so next week, Monday, Ben Way is going to give the lecture, and he'll show you how to compute the eigenvectors, which basically tells you how to compute the singular vectors. And we'll show this connection. And then on Wednesday, the lecture will be about extending this to PCA and things like MBS, which will be another application of the singular value.
So let me see.